In Chapter 6, we are going to use matrices and determinants to solve systems of linear equations. In Section 6.1, we're going to look at using matrices to solve systems. In Section 2, we'll continue using matrices to solve systems, but this time we're going to look at what happens if the system is either inconsistent or dependent. And in Section 6.5, we're going to use determinants, which are a calculation based on the matrix. It's just a constant, and Cramer's rule to solve systems of equations. All of this we're going to do on our TI-84 calculator, or if you've downloaded the TI-84 emulator, you can use that. That's what I'm going to use. In Section 6.1, first, we're going to write the augmented matrix for our linear system. It's important that we are able to do this, otherwise our calculator can't calculate the solution for us. Second, we are going to do a few row operations. These are going to be done by hand and not using your calculator. It's important that you understand how row operations work so that you'll know how your calculator is solving the problem for you. So we will then use matrices, our augmented matrix, and Gaussian elimination to solve systems. We're going to put our augmented matrix in row echelon form. That's Gaussian elimination. Then we'll use Gauss-Jordan elimination. That means we're going to put our augmented matrix in reduced row echelon form. Objectives 3 and 4, your calculator will do this. Your calculator will put an augmented matrix in row echelon form using Gaussian elimination, and it will put an augmented matrix in reduced row echelon form using Gauss-Jordan elimination. What's a matrix? Matrices are used to display information and to solve systems of linear equations. A matrix, the plural is matrices, is a rectangular array. In other words, you put information in rows and in columns. The values inside the brackets are called the elements of the matrix. So in this example we have at the bottom of the slide here, the elements of this matrix are, in the first row, we have 1, 2. So the first row, first column is the number 1. The first row, second column is the number 2. In the second row, we have 3, 4. So second row, first column is a 3. Second row, second column is a 4. And that is usually how we designate elements of a matrix. We designate it by its row first and then by its column. So for example, we could write something like A12. This represents the element that's in the first row and the second column. So the first number in your subscript tells you what row you're in. The second number in your subscript tells you what column you are in. So the element that's in the first row, second column, is a 2. The element in the second row, second column, which we would designate A22, would be 4. We also describe matrices by the number of rows and the number of columns that they have. In this example, I have 2 rows and 2 columns, so we would call this a 2 by 2 matrix. Because it has 2 rows, the first number represents the number of rows by 2, The second number represents the number of columns. So it's 2 by 2 matrix, 2 rows, 2 columns. All right, what's the augmented matrix? The first step in solving a system of linear equations using matrices is to write the augmented matrix. An augmented matrix has a vertical bar separating the columns of the matrix into 2 groups. The coefficients of each variable are placed to the left of the vertical bar, and the constants in your equations are placed to the right. If any variable is missing, its coefficient is 0. It's very important that you are able to create the augmented matrix from your system of equations. So here are 2 systems of equations, and we are going to write the augmented matrix for each of these systems. All right, so the first system we have, the first equation is 3x plus 2y plus 2z equals 31. The second equation is x plus y plus 2z equals 19. The third equation is x plus 3y plus 2z equals 25. So I'm going to create my augmented matrix. The first thing I'm going to do is to write a bracket. When I see this bracket, that tells me that this array of numbers is a matrix. All right, I normally create my augmented matrix by columns, but then I always check by rows. What do I mean? The first column of my augmented matrix is formed by taking the coefficients on my x terms. So the first column in my augmented matrix are the numbers, the coefficients on the x's. So the first equation, the coefficient on x is 3. So the first number in my matrix, first row, first column, is a 3. In my second equation, the coefficient on x is 1. So my second row, first column, is a 1. And then my third equation, the coefficient on x is 1. So my third row, first column, is going to be a 1. So this first column here, those are the coefficients on the x's. All right, now let's do the second column. The second column is going to be the coefficients on the y's. In the first equation, the coefficient on the y is the number 1. So my first row, second column will be a 1. These are going to be the y's. The second equation, the coefficient on y is 1. So my second row, second column will be a 1. In my third equation, the coefficient on y is a 3. So my third row, second column will be 3. The third column is going to be the coefficients on my z's. In the first equation, the coefficient on z is 2. So my first row, third column will be a 2. In my second equation, the coefficient on z is 2. So my second row, third column will be a 2. In my third equation, the coefficient on z is 2. So my third row, third column will be a 2. Now I'm going to draw a vertical bar to separate the coefficients on my x, y, and z's from my constant, and my fourth column will be my constants, which are 31, 19, and 25. So the augmented matrix you have formed has 3 rows and 4 columns. It's a 3 by 4 matrix. Now, I always check, once I've written my augmented matrix down, I check by rows. What do I mean? I'm going to look at that first row and make sure the first three numbers are the coefficients on X, Y, and Z. 3, 1, 2. I'm okay. The fourth element in that first row, I'm going to make sure that's my constant, 31. So the first row of my matrix is correct. Let's look at the second row. That should be the coefficients on X, Y, and Z in the second equation and the constant, 1, 1, 2, 19. I'm good to go. The third row should be the coefficients on my X, Y, and Z and my constant, 1, 3, 2, 25. 1, 3, 2, 25. So I am good to go. Now, why am I emphasizing this? Because you have one chance at this. Once you've put your augmented matrix in your calculator and you determine your solution to your system of equations, you get an answer. And if you haven't written the augmented matrix down correctly, or you haven't inputted it into your calculator correctly, you're going to get the wrong answer. So it's important that we check during these steps so that we get the correct answer when we're done. All right, so let's look at the second system of equations, and let's write down the augmented matrix. Going to write my bracket to show that I'm creating a matrix. I'm having sharing issues. Let me reshare here so we can see what I'm doing. There we go. All right, so the first column is going to be the coefficients on my X. All right, so the first equation, the coefficient on X is 1. But the second equation, the X term is missing. There is no X term there. So I'm going to input that into my matrix as a 0. So the second row, first column is a 0. As is the third row, first column. In the third equation, again, X is missing, so we're going to put that in our matrix as a 0. All right, so I have my first column done. Now I'm going to do my second column. The coefficient on the Y in the first equation is 2. The coefficient on Y in the second equation is 1. And there is no Y in the third equation. So I'm going to input that into my matrix as a 0. Now we're going to do our third column. Those are the coefficients on Z. We have -5 in the first equation, 3 in the second equation, 1 in the third equation. Draw a vertical bar and write our constants in our fourth column. And I'm going to do a quick check to make sure that I've written this down correctly. So the first row should be the coefficients on X, Y, and Z, and the constant, 1, 2, -5, -19. I'm good to go. The second row in my matrix should be the coefficients on my X, Y's, and Z's, and my constant, 0, 1, 3, 9. I'm good to go. Third equation, my third row in my matrix should be my third equation, the coefficient on my X, Y, and Z's, and my constant, 0, 0, 1, 4. All right, this second augmented matrix here is rather interesting because when we have this system of equations, the third equation is solved for Z. And if we look at the augmented matrix, the first two elements in that third row are zeros. So if we were to write the equation from the augmented matrix, go backwards, if you will, we would see that Z is 4. Well, now we know what Z is. So once we know what Z is, we can back substitute into the second equation and find Y. Once we know Y and Z, we can back substitute in the first equation and find X. This is significant. So what we normally do is we start with an augmented matrix like the top one, and we do row operations on our matrix to get it in the form of the second one. Once it's in the form of the second matrix on this slide, we can find Z, then find Y, then find X. This is called row echelon form, and we do that by using row operations. We're going to let our calculator do those row operations for us. But before we do that, let's look at some row operations. So here is what we're intending to do. Having sharing issues again. All right, so here's what we're intending to do. We're intending to use matrix row operations to force our augmented matrix into this row echelon form, where the main diagonal, and the main diagonal you start in the first row, first column, and go diagonally downward to the third row, third column. That main diagonal should all be the number 1. And then everything underneath those ones, will be zeros. So that's row echelon form. And normally you would do this by hand. You would take a matrix, you do row operations until you got it in row echelon form. However, it's so much faster to do it on your calculator. We're going to do it on our calculator. I promise we're going to do it on our calculator. But first, let's practice a few row operations. All right, what can you do? The first thing you can do to any matrix and get an equivalent augmented matrix is you can interchange any 2 rows. This is the same as taking your system of equations and writing 2 equations in a different order. And you can do that. There's nothing sacred about this has to be the first equation, this one has to be the second. You can write the equations in any order you want. The other thing you can do is you can multiply an entire row of an augmented matrix by a constant, or you can divide an entire row of an augmented matrix by a constant. This is the same thing as multiplying or dividing both sides of an equation by a number. And of course, this number has to be non-zero. You can't multiply both sides of an equation by 0. The third thing that you can do, and this is the one that's significant, is you can take a multiple of any row and add it to another. And this is very helpful when you're doing row operations by hand to get a 0 in the particular row and column that you need a 0 in. All right, so what can you do? You can interchange any 2 rows of a matrix. You can multiply an entire row of an augmented matrix by a constant or divide by a constant as long as it's not 0. And you can take a multiple of one row and add it to another. All right, so here is the designation for each of these operations. The first operation, interchanging any 2 rows, we write like this. So we have capital R sub I. I just tells you what row you're in. So if I is a 2, that's the second row. And a double arrow, and then R subscript J. J again just designates what row you're in. So J could be 1, 2, or 3, as could I, 1, 2, or 3. Multiplying any row by a non-zero constant, we designate that by K times R sub I. So you have a number like, we could write 3 R2. That means to take the entire second row and multiply it by 3. And then to add a multiple of one row to another row, we designate that by K times R sub I plus R sub J. So when you do this, you get a new row J. When you take a multiple of one row and add it to another row, that row that you're adding to it, you're changing that row. So this would give us a new row J. Okay, so let's practice. Let's just do a couple of problems using row operations. You've got a couple of problems in MyMathLab using row operations, and then we'll get to those calculators. Okay, so use the matrix 4, 12, minus 28, 1, 6, minus 3, 7, -3, -2, 1, -9, and let's do the indicated row operation. And what does that row operation say? It says to interchange rows 1 and 2. That means you simply flip them. So row 2 becomes row 1, and row 1 becomes row 2. So what would we get? We would get 1, 6, -3, 7. So I took the second row and made it the first row. 4, 12, minus 28. So I took the first row and made it the second row, and the third row stays the same. Put my line in there, put my brackets to designate that it is matrix. Now, why would you do something like this? Well, again, from previous slides, we saw that if we can put augmented matrix in row echelon form, that means the main diagonals are all ones and everything underneath those ones are zeros, we can solve the system pretty quickly by finding z, finding y, finding x. And we need to first get in the first row, first column, a 1, because we need that main diagonal to be 1s. We need this main diagonal to be 1s. And that's what that accomplishes that for me. All right, let's try another row operation. What does this row operation say? It says to take the entire first row and multiply it by 1/4. 1/4 R1. Take the first row and multiply it by 1/4. So we take every element in the first row and multiply it by the number 1/4. So what do we get? 1/4 times 4. That would be the first row, first column. 1/4 times 12. That would be the first row, second column. 1/4 times -20. And 1/4 times 8. And the other two rows stay the same. So what do we get? Well, we would get what? 1, 3, -5, 2, 1, 6, -3, 7, -3, -2, 1, -9. And I kind of ran myself out of room there, put my bar in there so I can separate those two. All right, and again, why would we do something like this? Well, for the same reason we did the row operation on the previous slide. We need that first row, first column to be a 1, and I could accomplish that by dividing the first row by 4. All right, our last row operation practice. What does this row operation indicate for me to do? This row operation says to take 3 times the second row and add it to the third row. This gives me a new third row. It doesn't change the first row. It doesn't change the second row. Adding a multiple of one row to another changes that row only. So what are we going to do? I'm doing nothing to the first two rows, but I am going to take this row, second row, I am going to multiply that by 3. And then I'm going to add that result to the third row. So I'm going to take the first element in the second row and I'm going to multiply it by 3 and I'm going to add it to the element in the third row. So I'm going to take 3 times 1 and add it to that element in the third row. I'm going to do the same thing to the second element in the second row. I'm going to multiply it by 3. So I'm going to get 3 times 6. Then I'm going to add that to the element in the third row, which is a -2. Do the same thing to the third element. 3 times -3. And I'm going to add that to the element in the third row. And then I do the same thing to the constant. 3 times 7 plus -9. So now what's my new third row? Let's see if I can write this rather neatly. Okay, so my first row is the same. Second row is the same. And what's my third row going to be? Well, 3 plus -3 is 0. 18 minus 2 is 16, I believe. -3 plus 1 is that -9 plus 1 is that -8. And then 27 minus 9 is that 18. Check my math real quick here, make sure I did that correctly. And I think I did not. 21 minus 9 is 12, isn't it? Yeah, well, this is 12. Can't add. Okay, so my new matrix is 4, 12, -28, 1, 6, -3, 7, 0, 16, -8, and 12. And why would I do something like this? Well, again, to put this matrix in row echelon form, the main diagonals have to be 1s, and everything underneath it has to be a 0. So you would want to get the third row, first column to be a 0. All right, so we've practiced row operations. So that's what row operations are for. They are to take an augmented matrix and force it in row echelon form. Once it's in row echelon form, you can back substitute and solve the system of equations. So here's the step-by-step method for solving a system of equations using Gaussian elimination and row echelon form. Write the augmented matrix. And now, instead of doing step 2 the way they do step 2, we're going to take our augmented matrix and put it in our calculator. And let our calculator do the row operations for us and put it in row echelon form. Once it's in row echelon form, we can do step 3, which is back substitute, find y and z. Y and x. All right, so let's put this system of equations. Let's write the augmented matrix, and then let's put this in our calculator, and then let's back substitute to find y and x. All right, so let's write the augmented matrix. This is a very important step. I can't overemphasize how important it is that you get this written down correctly. So I write it down in columns, the coefficients on the x, 2, 1, 1. Coefficients on the y's, 1, -1, 2. Coefficients on the z's, 2, 2, -1. And then my constants, 18, 9, and 6. And then I'm going to check it by rows. The first row should be 2, 1, 2, 18. Second row should be 1, -1, 2, 9. 1, -1, 2, 9. And the third row should be 1, 2, -1, 6. 1, 2, -1, 6. So I am good to go. I'm ready to put this in my calculator. So I'm going to share my TI-84 emulator. All right, so I need to input this augmented matrix into my calculator. So I need to find my matrix menu. And it depends on if you have a TI-84 or a TI-83, where the matrix menu is. Since I'm using a TI-84, I'm going to show you where it is on the TI-84. You need to find it on the TI-83 yourself, and it should be its own button in the TI-83. But on the TI-84, the matrix menu is above the inverse button. So it's right here above the x to the -1 matrix in blue. So we have to use our second key to get to the matrix menu. So I'm going to go second. Oh, did the wrong one. Sorry about that. Yeah, clear that out of there. Made a mistake. Second, -1. So here we are in our matrix menu. The first column in our matrix menu is just the names of our matrices. We have 10 matrices available to us in the calculator. So we can input 10 different matrices. The second column, I'm going to arrow to the right, is our math menu. And this is where we're going to find row echelon form once we input the matrix. Number one, we're going to use in section 6.5. That's determinant. So we'll do that in 6.5. But right now, I need to input the matrix. So I'm going to arrow over one more to edit. And this is where I'm going to input that augmented matrix. So I'm going to hit enter because I'm going to put this matrix in A. So hit the enter key. All right, so the first thing that the calculator asks you is how many rows and columns are there in your matrix. We have a 3-row, 4-column matrix. So it's a 3 by 4. So I'm going to click 3, enter, then 4. And you can see that my calculator creates a 3-row, 4-column matrix for me. Now I'm going to input each element in this matrix. And my calculator takes the elements by rows. So the first row, first column in my augmented matrix was a 2. So I'm going to click 2, enter. And it takes me to the second column in my first row. And I'm going to input that number, which was a 1. And the first row, third column was a 2. And the first row, fourth column was 18, the constant. And when I input that, it drops me down to the second row, and I continue inputting the elements in the second row. So I had 1. All right, so the next element is a -1. Be sure you use your negative key, not your minus key. So -1, enter, 2, and 9. So now we're going to do the third row. 1, 2, -1, and 6. All right, so when I hit enter on the 6, it took me back to the first row, first column. All right, so I have my matrix in, and I'm going to do a quick check to make sure that I have everything in the matrix correct, and it looks correct to me. If it wasn't, I could just use my arrows and arrow to this whatever element I had incorrect, and I could correct that. Right, so once I have the matrix inputted, I need to exit the matrix menu. I have to get out of here and then go back in. I know it doesn't sound real intuitive, but I have to do that. So I'm going to do a second quit. I have to exit the matrix menu. All right, so now I'm back on my home screen. Now I'm going to go back in the matrix menu, and I'm going to put that matrix in row echelon form. So I'm going to go second, inverse, get back to my matrix menu, and there you can see where I've inputted that matrix A. There it is. I'm going to arrow over, and then I'm going to arrow down till I find A, R-E-F, row echelon form. So my calculator is going to use Gaussian elimination and put my matrix in row echelon form. So I'm going to click enter, takes me back to the home screen. So now it's waiting. What matrix do I want to perform row operations on, and put it in row echelon form, matrix A. So I'm going to go back to my matrix menu, and now I'm just going to hit enter, and that will bring matrix A back to my home screen. Close my parentheses because that's a good habit to be in, and now I'm going to hit enter. And if it's placed my augmented matrix in row echelon form. The main diagonal, first row, first column is a 1. Second row, second column is a 1. Third row, third column is a 1. Every element underneath those 1s are zeros. It's in row echelon form. Now it's fractions, which I'm not real happy about. It's decimals. So I'm going to change this to fractions, all right? So this is what you're going to do. You're going to go to your math menu, the math menu, over here on the left. Number 1 is fraction. It's going to change your decimals to fractions. So I'm going to click enter. It's going to take this matrix and write it as fractions. I hit enter. And there's my row echelon form matrix. First row, 1, 1/2, 1, 9. Second row, 0, 1, negative 2/3, 0, 0, 0, 1, 3. So from the third row of this matrix, when I go back and write the system of equations, I can determine z. Z is 3. All right, let's go back and share our PowerPoint. Let's see if we can't back substitute and find y and x. All right, let me share. All right, so here is the augmented matrix in row echelon form. So we're now going to write this row echelon form matrix back to a system of equations. So this third row, x, the coefficient on x is 0, the coefficient on y is 0, but it tells me that z is 3. So I know what z is. Now I'm going to write this second equation, and I'm going to do this down here, just so I have a little room. Okay, this says 0x plus 1y minus 2/3 z is equal to 0. But I know what z is. Z is 3. So I'm going to replace z with 3. I get y minus, the 3's will cancel, 2 is 0. Add 2 to both sides, and I get y is 2. All right, next I'm going to take this top row and write the equation that fits that top row. I have x plus 1/2 y plus z equals 9. Remember, those elements in that first row in my augmented matrix represent the coefficients on my x, y, and z and my constant. Now I'm going to back substitute to the two values I have for y and z. So I have x plus 1/2 times 2 plus 3 is equal to 9. The 2's cancel here, and I'm left with a 1. So I get x plus 4 is 9, subtract 4 from both sides, and x is 5. So what is the solution to this system of equations? The solution to the system of equations is the ordered triple, x, y, z. So the solution is 5, 2, 3. All right, that was fun. I'm going to show you Gauss-Jordan elimination, and you'll never use Gaussian elimination again. Gauss-Jordan elimination, what you do in Gauss-Jordan is you get the main diagonal to be 1s, just like you did in Gaussian elimination, but then you're going to get the elements below and above to be 0. And when you use Gauss-Jordan elimination, you put your matrix in what's called reduced row echelon form. The main diagonal is 1, everything else is zeros, so you should be able to just look at the matrix in reduced row echelon form and determine what z, y, and x are. Let me show you what I mean here. Okay, this is the same system of equations that we solved using Gaussian elimination, putting it in row echelon form. Now let's go back to our calculator and let's put this matrix in reduced row echelon form using Gauss-Jordan elimination. So let me share my calculator. All right, so here we are back at the calculator. And now I'm going to take the same matrix and I'm going to put it in reduced row echelon form. So I'm going to go back to my matrix menu, second inverse. I'm going to go over to math and I'm going to go down till I find RREF, reduced row echelon form. Hit enter. Okay, now what matrix am I going to put in reduced row echelon form? Well, the only matrix I have inputted right now is matrix A. So I'm going to go back to my matrix menu, hit enter, close my parentheses, and hit enter. So this is going to take my matrix A, that augmented matrix, and put it in reduced row echelon form using Gauss-Jordan elimination. That's a mouthful. So I'm going to hit enter, and there you go. So the new augmented matrix is 1, 0, 0, 5, 0, 1, 0, 2, 0, 0, 1, 3. So from the third row of this matrix, you know that Z is 3. The second row of this matrix, the coefficient on X and the coefficient on Z are both 0. So you have Y equals 2. In the top row, row 1, you have 1, 0, 0, 5. So the coefficient on Y is 0. The coefficient on Z is 0. So that tells you that X is 5. So if you put your augmented matrix in reduced row echelon form, the column, the fourth column, is the solution to your system. The first number in the fourth column is X. The second number is Y, and the third number is Z. And that concludes section 6.1. We'll continue in section 6.2 using our calculators to put our matrices in reduced row echelon form or row echelon form and show you what happens if the system is inconsistent or if it's dependent.